Okay, now we're talking about this problem, the magnetic flux density. Flux density can be calculated flux divided by area. So here is a area here. From this area, the magnetic flux are coming out. This area is A. So flux density can be calculated P equal to 5 by A. Phi is a flux. Magnetic flux unit is a Weber. A is a cross-sectional area. Unit is a meter square. And B is flux density. Unit is a Tesla. So flux density can be calculated magnetic flux divided by area. So the phi is a unit of Weber, A is a cross-sectional area meter square, and B is a flux density, unit is a Tesla. So this is the way we calculate the flux density. So that based on this one, we saw the one problem. The flux produced by magnet is a 10 milliweber. When you determine the flux density, if the area is a 250 millimeter square. In this case, we can see here flux phi. Flux phi is 10 milliweber. So 10 into 10 power minus 3 Weber. This is the 10 milliweber. Area A is 250 millimeter square. So 250 millimeter square, so 250, 1 millimeter equal to a 10 power minus 3 meter. So this is 250 multiplied 10 power minus 6 meter square. Then we can calculate the flux density B 5 by A. So phi is 10 multiplied 10 power minus 3. A is 250 multiplied 10 power minus 6. Therefore, the 10 multiplied 10 power minus 3, 10 power minus 6 go to numerator. So this is 10 power 6 divided by 250. So this is the 10 multiplied 10 power 3 divided by 250. So we got the 40 Tesla. This is the answer is 40 Tesla. And next problem. So in this case, we have to calculate if area is at 300 millimeter square, we need to calculate the flux density. So now flux is unchanged, 10 into 10 power minus 3 Weber. Area is now is 600 millimeter square. Then we need to calculate the flux density. Phi equal to B equal to 5 by A. So phi is 10 into 10 power minus 3. Now it's 600 millimeter square, so this will be the 600 into 10 power minus 6. So that will be 10 into 10 power minus 3 multiplied 10 power 6 divided by 600. By solving this one, that will be 16.7 Tesla. The flux density is 16.7 Tesla we got. And also we also need to calculate the flux. Next problem. Flux density B is given the 2 Tesla. Area is 300 millimeter square. We need to calculate the flux. So in this case, we write down the equation. B equal to 5 by A. Therefore, phi equal to B multiply A. Flux density multiply area, we can calculate the flux. So then we calculate So that will be the B is 2 Tesla, area 300. 10 power minus 10 millimeter square is a 10 power minus 3 square. So this is fine, can be calculated. That will be the 600 into 10 power minus 6 Weber, or 600 microweber. This is the way we calculate the flux. The next will be electromagnetism. So now we can calculate the magnetomotive force. If you connect the battery to the resistor, the electric current will flow. Battery voltage is E, current is I, resistance is R. So E can be calculated I multiply R. I is current, I is resistance. Similarly, here is a magnetic coil. This is a magnetic coil. When you electrical current flow into the coil is a number of turn N. Then we can produce a magnetomotive force, MMF. It's a current multiply number of turns. This is the way we calculate. M is a MMF is a magnetomotive force similar to the voltage. I is electrical current flow into here, and N is a number of turns. So that those magnetic flux are passing through to the iron bar. So that was the flux going through. So this iron bar called the magnetic reluctance, REL. REL is reluctant. The unit is an ampere turn per Weber. So that MMF is equal to flux phi multiply reluctance. Phi is a flux, unit is a Weber. REL is reluctant, this is MMF. So similar to the voltage source. When the electrical current flow to the resistor, current multiplied resistance is equal to the supply voltage. Similarly, the magnetomotive force. Magnetomotive force can be calculated. So this is the coil. So current flow to the coil with number of turn N. So the I multiply N is a magnetomotive force. This magnetomotive force is equal to flux multiply reluctance. Reluctance is similar to the resistance. So the phi multiply reluctance is also equal to the magnetomotive force. This is the way we calculate the magnetomotive force. So based on this one, now we solve the problem. The coil of 120 turns has a current of 250 milliampere. So we have to calculate magnetomotive force produced by the coil. So in this case, the coil number of turns given the 120 turns. The current flow to the coil is 250 milliampere. We need to calculate magnetomotive force. N is 120, I is 250. We need to calculate magnetomotive force. So we calculate MMF equal to M multiply I. And 120, current is 250 milliampere change to the ampere, so multiply 10 power minus 3. By solving this one, we got that 30 ampere turn. 30 ampere turn we got. The next one. So that in the power supply question 1, current limitation of 120 milliampere, how many such turns can be varied by maintaining same magnetomotive force? This means we want a magnetomotive force 30 ampere turn. But the current is only the 120 milliampere can be allowed to flow. So we have to calculate how many number of turns. So that we calculate MMF equal to M multiply I. Then N equal to MMFII. So MMF is 30. Current 120 into 10 power minus 3. So that will be the, because of that we change the milliampere to ampere, so that multiply with 10 power minus 3. So this is N also equal to the 30 into 10 power 3 divided by 120. So you got, what we got is a 250 number of times. So that we need the additional time because originally is 120, so the additional time can be calculated. $250 minus 120, so we need 130 times more. Additional time is 130 times. The next one, next problem. The coil is given. The coil is magnetic force. Magnetic force value is 125 ampere turn. MA is 125 ampere turns given. Number of turn N, 1000 turn. We need to calculate the current. How much current need to be like flow? So in this case, MMA is 125 ampere turns. Number of turns is 1000. So that we need to calculate the current. So we write down the equation. MMF equal to M multiply I. Then I can be calculated MMF divided by N. So MMF is 125. Number of turns is 1000. So the current value is 125. So this is the 125 into 10 power minus 3 ampere or 125 milliampere. So this amount of current need to be flow and need to flow so that we can maintain the kind of magnetic force. So the next one is a number of tap-ins are here. 1, 2, 3, 4, 5 tap-ins given. So that will be the tap-in 1, tap-in 2, tap-in 3, tap-in 4, and tap-in 5. Both tap-ins are given. So each tap-in has a 35 times. So this one called a 35 times, 35, 35, 35. So 35 times given. So we had to calculate, so that will be the, we need to calculate a magnetic force. Current flow in the coil is 2.5 ampere. So this current is a 2.5 ampere. So this 2.5 ampere flowing from here to here. So that now we can calculate 1 to 2. 1 to 2. So that current and number of time. So current 2.5. 1 to 2 is only 35 times. So that will be, what you got is 87.5 ampere turn. 1 to 2 is 87.5 ampere turn. And we also need to calculate 1 to 2 and 1 to 3. So 1 to 3 is how many ampere turn? 1 to 3 is 35, 70. So they say I multiply N. The current is 2.5. Ampere turn is 70. So what you got the thing is, that will be the 175 ampere turn. That will be 175 ampere turns. And 1 to 4. 1 to 4 is I into N. I multiply N. So current is a 2/5. Number of time is a 105. So that will be the 2/5 multiplied 105. You call it 262/5 ampere turn. 262/5 ampere turn we got. And then we need to calculate 1 to 5. I multiply N. Current 2/5. Number of time is 140. So by solving this one, we got the thing is 350 ampere turn. So this is the way we calculate the ampere turns. Okay, the next one will be the next problem. So we have to calculate the flux. In this case, number of time is 1000 times. So I got the number of time N 1000. And the current flow is 1.5 ampere. And reluctance, REL, is equal to 45000 ampere turns per wave. So this is the equation given. Therefore, then we need to calculate. Firstly, we have to calculate the magnetomotive force, MMF. So M multiplied I. And it's a 1000 and then 1.5. So 1500 ampere turn. This is magnetomotive force. Then we have to calculate the flux. Flux equal to MMF divided by reluctance. So MMF is 1500. Reluctance is a 45000. So by solving this one, there will be the so this is the 33.3 into 10 power minus 3. So this is Weber or 33.3 milliweber. This is the answer. So we also need to calculate the next problem. We have to calculate how much current flow. We have to calculate the current. In this case, coin 1500 tons. Number of time N 1500. Number of time N is given 1500. Flux is 15 milliweber. Phi equal to 15 milliweber. So 15 multiplied 10 power minus 3 Weber. The flux is a 15 multiplied 10 power minus 3 Weber given number of times 1500. We need to calculate the current. So in this case, reluctance. Reluctance is a 5000 ampere turns per Weber. Okay, so if you know the flux and if you know the reluctance, you can calculate the magnetomotive force. MMF equal to 5 multiplied reluctance. Find the reluctance multiply, we can calculate the magnetomotive force. So in this case, our flux is the 15 milliweber, 15 into 10 power minus 3. Reluctance value is given. Reluctance is a 5000. So that will be the magnetomotive force become the 75 ampere turn. Then we need to find the current. So the MMF equal to and multiply I. So that I equal to mmf divided by n. So magnetic force is 75. Number of time 1500. So that will be the so 1500 75 by 1500. So this is equal to the 0.05 ampere. So this is the way we calculate it. The next problem. The next one, magnetic circuit. Core area 250 millimeter square, flat density 2 Tesla. Reductance is 60,000 ampere turn per Weber. We need to determine the current. So in this case, our area is given 250 millimeter square. Number of turn and its flat density is 2 Tesla. Reductance is 60,000 ampere turn per Weber. We need to calculate the current and coin got the 6,000 number of turn. So those are the given. Area 250 millimeter square, flat density is 2 Tesla, reductance is 60,000 ampere turn per Weber. We need to calculate current and number of times the 6,000. So the firstly, we have to calculate flux. And flux multiplied reductance, you can got the magnetic force. Then the magnetic force divided by the number of times we can calculate the current. So this is the way. So firstly, we have to find the flux. Phi equal to B multiply A. Flux density multiply area of the core, then you can calculate the flux. So in this case, the flux density is 2 Tesla. Area is 250 millimeter square, so 10 power minus 3 square. So the 500 into 10 power minus 6 Weber. This is a flux. And the flux multiply reluctance, you got the magnetic force. Magnetic force equal to flux multiply reluctance. The flux is 500 into 10 power minus 6 Weber. And reluctance is 60,000. So by this way, we can calculate the magnetic force. There will be the 30 ampere turn. Then this MMF equal to the number of turn multiplying current. Therefore, we can calculate the current MMF divided by number of turn. So NA 30, number down is 6,000. So then we can calculate current. Current will be the 5 milliampere. So this is the way we can calculate current. Next problem. Electromagnet has the core length of the 400 millimeter. One with the 2000 number of turn, carry the current 200 milliampere. We need to calculate magnetizing force. So in this case, we can find the magnetizing force. Magnetic force is unit is an ampere turn. This is for the current multiply number of turn. So that this is the coin here. This is number of time. Current flow is a I. And this coin got the leg of the L. So that we can calculate magnetizing force. So magnetomotive force divided by leg L. So this is the Ni by L. Unit is ampere turn per meter. So magnetizing force can be used as H. So this is the magnetizing force. This magnetizing force and flux density also related. Flux density is a B. Magnetizing force is a H. And permeability is a mu. So we write out the equation B equal to mu H. This is a relationship. So the magnetizing force can be calculated number of turn multiply current divided by length of the coil. So Ni by L, this is the magnetizing force. Magnetizing force unit is ampere turn per meter. This magnetizing force and the flux density are also related. B equal to mu H. In this case, B is the flux density. Tesla A is the magnetizing force. Unit is ampere turn per meter. Mu is a permeability. This permeability is a depend the magnetic capability of the materials different from the one material to another material. So this is the way we calculate B equal to mu H. That's the problem. So we have to calculate the current flow into the coil 600 times. So number of times is 600. The current is, we have to find the current. Magnetizing force is 2000 ampere turn per meter. H equal to 2000 ampere turn per meter. And length of the coil 150 millimeter long. A 150 millimeter. So 150 multiply 10 power minus 3 meter. This is the given. So firstly, we write down the equation H equal to Ni by L. The equation. So H equal to 2000. Number of turn is a 600. Current I. L is 150 into 10 power minus 3. Then we can calculate the current. 600 I equal to 2000 multiply 150 multiply 10 power minus 3. Then I can be calculated 2000 multiply 150 multiply 10 power minus 3 divided by 6000. So this is the way we calculate. Then will be the current is, what you got the thing is 0.5 ampere. So this is the answer. The next problem. The magnetic core is at 300 millimeter. Cross-sectional area is 500 millimeter square. Permeability 125.7 into 10 power minus 3. So we also need to calculate the current. Reluctance is a, we have to find the reluctance. So this is the magnetic core. L 300 millimeter. So 300 into 10 power minus 3 meter. Cross-sectional area 50 millimeter square. A equal to 50 millimeter square. So 50 into 10 power minus 6 meter square. Permeability 125.7 into 10 power minus 3. mu 125.7 into 10 power minus 3. We have to calculate reluctance R. So in this case we can calculate reluctance equation. They are resistivity and permeability. This is the resistor. Resistance can be calculated rho L by A. Rho is resistivity. A is a length. A is a cross-sectional area. R is resistance. So this is the equation to calculate the resistance of the conductor. R is resistance. Rho is a resistivity. A is a length. A is a cross-sectional area. Resistance can be calculated. Similarly, we can also calculate reluctance. Reluctance equation is L by mu A. The equation. A is a length. A is a cross-sectional area. Mu is a permeability. So this is the equation to calculate the magnetic reluctance. In the electrical circuit, the voltage is forcing the current to flow. Resistance opposes the current flow. Similarly, for the magnetic circuit, magnetomotive force is forcing the flux to flow. Reluctance is opposing the current flow. This is that reluctance can be calculated. Reluctance equal to L by mu A, this formula. Therefore, this problem, length is given at 300 millimeter, area is 50 millimeter square, U value is at 125/7. Then we can calculate reluctance. Reluctance equal to L equal to 300 into 10 power minus 3, area is 50 into 10 power minus 6, mu is a, so this is a and a mu value is 125/7 into 10 power minus 3. So this one we are solving. So that will be the reluctance equal to, so that will be, yeah, this and this cancel. So 300 into 10 power 6 divided by 50 into 125/7. So this one we got. So by solving this one, what you got is 47732 ampere turns per wave. So the answer is 47732 ampere turns per wave we got. Then the next problem here. This is a magnetic coil is given here. Magnetic coil is given. So the windings are wound on the core. And it's a 240. Current I need to be calculated. Plus phi, the flux is flowing. Phi equal to 250 milliweber. This is given. Phi is 250 milliweber. I need to be calculated. In this case, number of time is 200. So those things are we given. So in this case, cross-sectional area, length of the magnetic flux is, core length is 150 millimeter. permeability mu equal to 100 into 10 power minus 3. And also the cross-sectional area, the core is 250 millimeter square. So those things are given. So that will be 250 milliwave by 250 into 10 power minus 3. Here is 250 into 10 power minus 6 meter square. Here is a waver. And also 150 millimeters. So A equal to 150 into 10 power minus 3 meter. Those things are given. So firstly, to calculate the magnetic force, we have to calculate reluctance first. Reluctance multiplied flux, then we can calculate the magnetic force. So reluctance can be calculated A by mu A. So that is a 150 into 10 power minus 3. Mu value is 100 into 10 power minus 3. Area is 250 into 10 power minus 6. Those things are given. So we can calculate the reluctance value. So reluctance can be calculated. Reluctance equal to A by mu A. So that will be here. So this 10 power minus 3. This one cancel. So the 150 into 10 power 6. Denominator 100 multiply 250. So then we calculate 150 multiply divided by 250. So 6 rounded. And we are done by waver. This is a reluctance. Then magnetic force can be calculated. MMF equal to flux multiplied reluctance. So flux is, we got the flux 250 into 10 power minus 3 waver. Reluctance is 6 rounded. So therefore that will be 250 multiplying 6. So 1500. And we are done. Then we calculate the current. So I multiply N is equal to MMF. So that now I can be calculated MMFI number of time. So magnetic voltage for you 1500, number of time is 240. Then you can calculate the current. Current value will be the 1500 by 240. So that will be number of time 240. So this is 1500 divided by 240. So 6.25 ampere. So this is the way we calculate current 6.25 ampere. Then we can also draw the magnetizing cut here. This is a magnetizing cut. For instance, there is a magnetizing force here flux density. When you increase the flux density, magnetizing force flux density will increase. But one time it's called the saturation. So this is the saturation point. So this one is a retentability. Retentability. And all those are you remove the magnetic flux. The magnetic flux is a still magnetic density still remain. So this will be a residual magnetism. So that if you go to the opposite way, the flux density also go down this way here. This is the saturation in the opposite point. So that these points are there, we have to remove them. You have to remove the magnetizing force and magnetic flux density. We have to provide the opposite force. This is the we call the conservativity. Conservativity. So this point. So this is for the pH gun. pH gun characteristic. Okay, the next one is induced voltage in a magnetic coil. Induced voltage. Induced voltage can be calculated E equal to PLV. E is a voltage for B is flux density. Tesla. A is a length. V is a velocity. Meter per second. That is a meter. So this is the E equal to PLV equation. We also calculate. And also the induced voltage can also calculate E and d5 by dt. Number of time multiply rate of change of flux, then we can also calculate the voltage. Also the voltage can also be calculated L di by dt. A is an inductance multiply rate of change of current. So that also calculates. So this is the N is a turn, number of turns. d5 by dt, change of flux. Wave per second. di by dt, change of current. So E equal to N d5 by dt or E equal to L di by dt or E equal to PLP. This is the way we can calculate this out induced voltage. So the next problem, the conductor hits the 250 millimeter long, move at the right angle with a velocity 20 meter per second. Magnetic field flux density 1.5 Tesla. We have to calculate the E and F. So this is the problem here. Length is 250 millimeter. So 250 into 10 power minus 3 meter. Velocity V 20 meter per second. Magnetic field flux density B is 1.5 Tesla. We have to calculate the E. So E can be calculated PLV. B is 1.5. A is 250 into 10 power minus 3. Velocity is 20 meter per second. So by solving this one, the voltage can be calculated is 7.5 volt. The next problem. Determine the velocity of conductor 200 millimeter length moving at the uniform speed through a magnetic field of the 1.25 Tesla at the right angle to produce the voltage of 500 millivolt. So in this case, E equal to 500 millivolt. So this is 500 into 10 power minus 3 volt. And flux density B equal to 1.25 Tesla. And the length is a 200 millimeter. So 200 into 10 power minus 3 meter. So this is the given. E 500 millivolt or 500 into 10 power minus 3 volt. Flux density B is a 1.25 Tesla. Length of the conductor is 200 millimeter or 200 into 10 power minus 3 meter. So we had to calculate the velocity. So that we write down the equation E equal to BLV. Therefore, V equal to E by BL. So V equal to E 500 into 10 power minus 3. And B is 1.25. Length is 200 into 10 power minus 3. So that will be the 1 millisecond. 1 meter per second. So this is the velocity we calculated. Next one. Next one is given the conductor long is 25 millimeter. So 25 into 10 power minus 3 meter. Conductor got the length 25 millimeter. It cuts through the flux at right angle. Velocity is 15 meter per second. Velocity V 15 meter per second. To produce the voltage 6 volt, E equal to 6 volt. So we had to calculate the flux density V. So that determine the flux density of the magnetic field of the conductor, 25 millimeter long, cuts through the flux at a right angle with the velocity of 15 meter per second to produce a voltage of 6 volt. We have to calculate. In this case, we write down the equation E equal to VLV. V can be calculated E divided by LV. So E is 6 volt. Length of conductor is 65 into 25 to 10 power minus 3. Velocity is 15. Then we can calculate flux density B. That will be the 20 Tesla. So this is 16 Tesla. Okay, the next problem. A coin of the $150 die with a flux of 300 milliweber. So this is N equal to 150 tons plus 300 milliweber. So 300 into 10 power minus 3 Weber. So the flux is reduced to 100 milliweber in 100 milliseconds. So we have to calculate induced voltage. So that this one is a 300 milli to go down to the 100 milliweber within 100 milliseconds. So we have to calculate voltage. So we calculate E. E equal to N d5 by dt. and 150 D5 300 minus 100. So V bar is 10 power minus 3. Time is within the 100 millisecond. So that will be, by solving this one, we got is 300 volt. So this is the answer. And another one is that this is the transformer given. Transformer got a 2 magnetic coil. This is primary coil. Here is secondary coil. 2 coils are given. Primary turn is a 300 turn, secondary is a 50. So here is a Ni is 300. So this is N. 2 is N1 is a 300, N2 is a 50 turn. Given. So Komoko got a flash 25 milliweber. We change to 5 milliseconds. We have to calculate the voltage. So the flash is changed. Flash change from the 25 milliweber to 0. The time is 5 milliseconds. Okay, so in this case, we can calculate primary voltage E1, secondary voltage E2. E1 equal to N d5 by dt. So the N is a 600. Chain of flight 25 milliweber to 0, 25 to 10 power minus 3 times the 5 milliseconds, so 10 power minus 3. So this will be the voltage will be 3 kilovolt, 3000 volt, or 3 kV. And also E2 and d5 by dt. Number of time is 50, d5 by dt is 25 into 10 power minus 3 divided by 5 into 10 power minus 3. So this one voltage will be the 250 volt. So this is the way we calculate the voltage. Primary and secondary voltage we can calculate. That is why we are talking about the meter. Okay, so the meter calculation. Galvanometer resistor 75 ohm, full scale deflection current is 2.4 milliampere. So for the meter, this is for the meter here. Meter will show the current, so this is meter current IM. But if the supplying current is greater than the meter current, we need to calculate the shunt winding. So this is RSH. In this case, we can see the current into shunt IAH. Meter current is IM and meter they say RM. So in this case, IM RM equal to ISH RSH. Also, total current I equal to IM plus ISH. There's an equation to calculate the meter current. IM plus ISH, this is the total current IM equal to ISH RSH. It's the equation. So based on here, we solve the problem. Galvanometer with the resistance 75 ohm. So in this case, RM is given the 75 ohm. Full scale deflection current 2.4 milliampere. So this is IM equal to 2.4 milliampere. So 2.4 into 10 power minus 3 ampere. We have to calculate the resistance of shunt required to use a meter is 100 milliampere meter. So the meter can only allow the 2.4 milliampere, but to the current here, this is meter here, meter only allow the IM is 2.4. but total current is 100 milliampere. So we need to calculate the shunt. So shunt resistance need to calculate. In this case, meter resistance is at 17.5 ohm. So that we see a 100 milliampere flowing, 2.4 go to the meter, so that the rest of the current ISH can be calculated. ISH equal to 100 minus 2.4. So you got the 100 minus 2.4. That will be the 97.6 milliampere. Or 97.6 into 10 power minus 3 ampere. So that this voltage, this is a parallel connection. Voltage in the meter is equal to voltage in the shunt. The voltage in the meter can be calculated Im into Rm. Voltage into shunt is ISH into RSH. So Im is 2.4 into 10 power minus 3. Rm is got a 17.5 ohm. ISH 97.6 into 10 power minus 3. And then we can calculate the RSH. So the RSH need to be calculated 2.4 into 10 power minus 3 into 17.5 divided by the 97.6 into 10 power minus 3. Then you can calculate RSH. Shunt resistance is can calculate 2.4 multiply 17.5 divided by 97.6. So you got the so that will be 0.430. And then now we also have to calculate resistance multiplier to use a meter as a 100 volts. So this is the resistor RSE. This meter resistance Rm. So meter only allow the 2.4 milliampere. So that this is that we can calculate. We have to use a voltmeter 100 volt. So RSE can be calculated. So VSE equal to 100 minus so the Im into Rm. So total voltage drop minus meter voltage drop, you got the series resistance voltage drop. So the 100 multiply Im. Meter current 2.4 into 10 power minus 3 resistance 17.5. So then we calculate it. 2.4 multiply 17.5. So 42 millivolts. So 42 is 100 minus 0.042. So you got the 99.95. This is VS0. Then we can calculate RSE equal to voltage is at 99.95. Current is 2.4 milliampere. So 99.95 multiply 1000 divided by 2.4. So you got 46 kilo ohm. We have to get 46, 41.6 kilo ohm. That should be you calculate. And also the sensitivity. Sensitivity can be calculated. Sensitivity is a resistance divided by voltage. So resistance is resistance by voltage. Resistance we calculate is 41650 voltage 1000. So that will be 40. So 41655. So voltage is 100 volt. So the 41655 ohm per volt. This we calculate the sensitivity. The next one. The moment ion meter moment requires 3200 ampere times the current 5 ampere. Then we have to calculate the number of turns. So this is the ampere turn is equal to the 3200 and current I is a 5 ampere. Then we have to calculate number of turns. So the ampere turn equal to N multiply I. Therefore, the N equal to ampere turn divided by I. So ampere turn 3200, current 5. So you have the 340 turn. So this is the answer. The next one, ammeter scale 0 to 150 milliampere. Use the appropriation to measure the full scale current 25 ampere. Scale reading is a 96 milliampere, whilst the current flow into the circuit. So this is the ampere here. Meter resistor. So meter scale is 96 milliampere. So in this case, meter scale 150 milliampere will get utilized. So when the full scale, the current is 150 milliampere. And this is the shunt. Full scale current is 25 ampere. So when the meter got the full scale deflection current is 150 milliampere. That time it can measure current up to 25 ampere. So this is the way. So that now we can, here you can see how much what is a meter resistance. Need to calculate. So that when 25 milliampere flow here, meter current is 150 milliampere. So now current is I is 16 milliampere flowing. Then we have to calculate. So that will be ratio. So when the meter show the 96 milliampere, so 150 milliampere. So that when the meter full scale depression 150 milliampere, the supply current is 25 ampere. If meter current is 96 ampere, what is the supply current? So this way, meter IM is 150 milliampere. To the current IT is equal to 25 ampere. If the meter IA 95 milliampere, what is the total current? So that will be 25 multiply 96 by 150. So we can calculate that will be the 16 ampere. This is the answer. And the last one, a galvanometer with a full scale depression, 2 milliampere, full scale depression voltage 6 millivolt. So we have to calculate resistance of the coil. So this means the meter voltage is equal to 6 millivolt. Meter current is 2 milliampere. So we have to calculate resistance. So the Vm by Im, the 6 millivolt by 2 milliampere. So you got the 3 ohm. Meter resistance, we call it 3 ohm. The total current in coil, total current in the circuit when connected to 0.125 shunt. In this case, we have to find out the total current. So that will be the, here is the meter here. We connect the shunt resistance 0.125. So we need to show the full scale depression. What is the total current? So in this case, the full scale depression, meter current is a 2 milliampere. Full scale depression. We have to find out the total current IT. What is the total current? So meter resistance is unchanged. This is the 3 ohm. Okay, so then we can find out the meter voltage. Vn is equal to the 2 milliampere multiplied by 3 ohm, so you got a 6 millivolt. This volt across here. So this is ISH can also be calculated. ISH is equal to voltage divided by RSH. So the voltage is 6 millivolt. RSH is 0.125. Then we calculate the ISH. So 6 divided by 0.125. So this is 48 into 10 power minus 3 ampere, the ISH. So therefore the I total can be calculated. Current in the meter is Im plus ISH. So Im is 2 milliampere, 2 into 10 power minus 3 plus ISH 48 into 10 power minus 3. So here 50 into 10 power minus 3 ampere or 50 milliampere. So the current flow into the meter is 15 milliampere. Then we also have to calculate the total current circuit when the meter indicates depression equivalent to 1/8 milliampere. So that when the meter shows there's a 2 milliampere, total current is 50 milliampere. So that when I enter 2 milliampere, I total is 50 milliampere. When the meter current is 1/8 milliampere, what is the total current? So this is we can calculate 5 multiplied by 1/8 divided by 2. So this will be the 45 milliampere. So this is 45 milliampere we got. In this case, the current in the shunt, ISH can be calculated. So the total current 45 minus meter current is 1/8. So the shunt current is a 43.2 ampere. So this is the answer.